So solubility curves. When I use the word solubility curves, this means that the solubility has been recorded in the form of graph. What we usually do is that we tend to dissolve that solid in a specific amount of water, as stated over here, and we do it at many different temperatures, and we keep on recording the amount of solid we were able to dissolve. By plotting this graph, we are able to call it a solubility curve. Now, most
Yes.
solids have solubility curves like those for the salts of shown in the figure. One of them is KCl, one of them is KNO3. They've specifically picked those salts so that they can explain to you in the form of a graph, in the form of a diagram, a salt which shows you a very little change in their solubility, KCl, or salt that shows you a good change in solubility over a change in temperature. So the same
Mm.
thing is stated over here. The solubility increased with temperature, either dramatically, they are trying to talk about KNO3 in this case, or just a little, and then they are trying to talk about KCl in this case. All right.
Yes.
Now, what can we do with solubility curves? What kind of questions can we face from solubility curves? They're going to talk about it next. So we can use solubility curves to work out what mass of crystals you would get if you cool a saturated solution. Now, before we move any further, let me tell you, if we can dissolve a higher amount of a solid at a higher temperature, and we move back to a lower temperature, that amount of solid will again undissolve. They'll like sit at the bottom. Now, what happens in actual, let me show you with the help of a diagram. Let's suppose we took a beaker, we pour in some of the liquid. Let's say the liquid is water. Since water is a universal solvent and a very good one at that, it can dissolve most of the substances that we can talk about. All right. So
Yeah.
we pour in some salt. Let's say we're talking about KNO3. We have started heating it up so that we can go to a higher temperature.
Mm.
Let's say that we started off with 20 degrees centigrade. And as you can see from this graph, and if I extrapolate this graph, at 20 degrees centigrade, we are able to dissolve like 30 grams, right? Let's
Yes.
say I started heating it up, I kept on adding salt, and we jumped all the way to 90 degrees centigrade. If I extrapolate this 90 degrees centigrade, it's a little closer to, let's say, 195 grams. Let's say I'm just assuming this value. It may not be the exact value, but I'm only assuming it. All right. So at 90 degrees centigrade, I'm able to dissolve 195 grams of salt. Now, whenever you throw in some salt in water, you'd notice that the salt will sit at the bottom. Now, we usually
Yes.
tend to use spoons or anything, stirrers or anything with which we can stir and dissolve the salt. Now, if you take a help of a stirrer and try to stir it, right, in order to dissolve the salt disappears after some time. We say
Mhm.
that the salt has dissolved. If the salt
Yes.
does not disappear, we say the salt is still undissolved, right?
Yes.
If it sits at the bottom, we say it's undissolved. If it disappears, we say it's dissolved. Now, what happens in these kind of questions is that they usually discuss moving from a higher temperature all the way to a lower temperature. Now, let's say after doing all of this, I brought the temperature down to 40 degrees centigrade. And at
Yes.
this temperature, after some of the stirring, the salt disappeared, which meant all 195 grams of it dissolved.
Mm.
At 40 degrees centigrade, when I brought the temperature back from 90 to 40 degrees centigrade, some of the salt sat at the bottom. I knew there was some undissolved salt, but I
Yes.
need to calculate that value. So these curves give us a very good idea, since we went on with different values at a time, since we never went from 20 to 90 in a single jump. What we did is that we went to 30 first, we noted the value, we went to 40, we noted the value, we went to 50, we noted the value, so on and so forth with 60, 70, and 80. So when we go from 90 to 40, we can already predict how much of this would settle down at the bottom.
Yes.
So yours ought to take this value and this value. Let's say this value is A, let's say this value is B. You're supposed to simply subtract B from A and you know the answer. Let's assume that A was 195. Let's assume the B is 65. You would instantly know that how much of it would be settling down at the bottom. Make sense?
Yes.
So this is what
Yes.
solubility curves are all about. We tend to give students the questions going from a higher temperature to a low temperature. And what we want them to do is to subtract the values of the salt dissolved per 100 grams of water so that they can give us the answer. The same thing has been done over here. Now, let's go through
Mm.
this example. Consider the solubility curve for potassium nitrate, KNO3. At 90 degrees centigrade, 200 grams of potassium nitrate dissolves in 100 grams of water. At 30 degrees centigrade, only 50 grams will dissolve. Therefore, if we cool a solution containing 200 grams of potassium nitrate in 100 grams of water, we cool it down from 90 to 30 degrees centigrade, 150 grams of potassium nitrate must be released from the solution, which it does as crystals. Now, this undissolved salt will actually form crystals at the bottom. So we use the word crystallizes out of the solution. This is the phrase that we commonly use.
How does the crystals like form?
Now, this is a common question from a student's mind. How does these crystals form? How do we know
Yes.
these are crystals? Now, what scientists or what we do as a common practice is that we don't get to know that these are crystals since there is some just undissolved salt settling at the bottom. What we do in order to find out that these are actually crystals is that we evaporate all of this water, so much so that we are only left with the salt, and then we take the salt and we look it under the microscope and we can actually are able to see the crystals with proper shapes. Now, when I
Mm.
talk about the word shapes, I hope you are familiar with many shapes from mathematics, from
Yes.
geometry: circles, squares, trapeziums, parallelograms, triangles, rectangles, the list goes on. You have studied many shapes in maths. So if we're
Yes.
talking about a crystal, it must have a specific shape, and we can always name this shape after looking at those crystals under a microscope. And that's what we do. That's why we have been using this phrase, crystallizes out of the solution, as a phrase as an answer. We sometimes also use the phrase precipitates out of the solution. Now, the precipitate actually word represents sudden formation of solid. The word precipitate itself means the sudden formation of solid. You'd notice there would be some undissolved salt at the bottom. Salt is a solid. The sudden formation of this salt, because we lowered the temperature down from 90 degrees centigrade all the way to 20 or 30 degrees centigrade, formed a solid at the bottom. We use the phrase precipitates out of the solution. Since this salt was previously a part of the solution, now the salt has been undissolved and is settling out at the bottom. Hence, the phrase precipitates out of the solution. Make sense?
Yes.
Great. So I hope now you understand how to do the maths. All right.
Mm.
And you also understand the phrases that we have been using for this purpose.
Yes.
Okay. Now, there is another hint, an important one at that. Because solubility varies with temperature, you must always quote a temperature with a solubility value. For example, for 195 grams, it occurred at a specific temperature. So quote the temperature along with the units, degrees and centigrades. 30
Can you
grams
repeat that?
happen every time you're quoting the mass of the salt that dissolved in water or in that liquid. You need to quote the temperature as well with proper units. Degree and
Yes.
centigrade are proper units. The number is important because that number tells us that at that specific temperature, this much amount is dissolved. Why?
Mm.
Note that at 10 degrees centigrade, there is a separate amount. At 20, there is a separate one. At 30, there is a separate amount. At 40, there is separate. At 50, there is something separate. So at every temperature, since the value is changing, so we need to count the temperature along with the value every time. So that
Yes.
any reader, anybody who is reading our stuff, maybe the examiner, maybe the one who's marking your exams, would know that the student understands that different values of salts dissolve at different temperatures. So whenever a student is talking about a value or amount of salt dissolved, he or she also mentions the temperature for the ease of understanding,
Mm.
right?
Yes.
For
Mm.
example, let me give you an example. We in our daily life go for understanding statements all the time. Let's say you sit in an exams, you take 90 marks in a specific subject, and I start telling your parents that you took 90 marks, and I don't tell them the subject, they'll get confused. Their first
Mm.
question would be, at least do tell us the subject she got 90 marks in. If she got 90 marks, was that science? Was that maths? Was that English? What was that? Right? So an
Yes.
explanatory statement is the one that completes the understanding of the listener or the reader or the one who is actually marking your exams. So you
Mm.
should be able to tell them the specific amount with the specific units, 30 in grams, the specific temperature with the specific units at degree centigrade. So that's the whole statement should look like. All right. So your whole statement should look like the solubility of sodium chloride, name or formula of the compound, at this specific temperature is this many grams in this many grams of water. So you give them the whole statement every time to understand the whole thing. They would
Mm.
understand the student knows what the name of the salt was, what the value of temperature was, what was the value of the salt that dissolved in, and what was the value of the liquid that we used, the solvent that we used for the dissolving purposes. So that's how you
Yeah.
should compose your sentences in exam, so the examiner should completely understand you. Sometimes the students assume he understand it was water. How would he or she know it was water? Here, he might understand that we are talking about 30 degrees centigrade. They don't even pretend to mention it. So look, if I'm not mentioning the subject, I'm also always just mentioning the marks, your parents would be irritated after asking a couple of times. And even then, I don't reply to them what subject it was, they would get irritated. What kind of person you are? You're just telling us the marks. You're not telling us the subject. What is this? A riddle? Are we supposed to guess it? All right. So they would get
Yeah.
irritated. What kind of statement is this? We don't get you. You need to explain yourselves. So the same thing happens with the person who is marking your exams. He always come up with the phrase that you're not making yourself clear in exams. So when writing, you should be writing all the things so that your sentences are clear for whoever is reading or marking your exams. All right. So don't
Mm.
assume stuff. Instead, write it in exams. Don't assume any of the things that the examiner would already know. Write them as a part of your answer. All right. I
Yeah.
hope now that this hint is also clear to you.
Yes.
And I trust me, I've seen a lot of students assuming stuff and not writing in exams. This is not a good way. How would the examiner know that you you're assuming that she or he would know this part as well as this part as well as this part? No, don't do that. Instead, come up with complete, understandable statements.
Yes.
Okay, now we have an example. Solubility is discussed for potassium chloride. It's KCl. There are different temperatures, 10, 30, 40, 70, 60. Now you can draw a graph. Now you would notice the graph has the value for 10, 30, 40, and then we have for 70, and then we have for 90. So
Mm.
what can you do is that you can extrapolate for the values that you require. We're missing a value of 50 over here, a value of 60 over here, a value of 80 over here, a value of 20 over here. So you can work your way with this chart for the value of 20 or for 50 or even for 60, all right, or even for
Mm.
80. That's what we have been doing. So if we missed a value in between, a graph always helps us to find out that approximate value. Let's say you were doing this experiment. You started off with noting the value for 10. Then you started talking to your friend and you missed out the point at 20. And then at 30, you noted down the value. Then you started chatting with your friend again. You're really chatty that day, that specific day. You missed out another
Yeah.
value at 50 and 60. So this graph will help us to put in the missing values. And a graph like
Yes.
that may come as a question. So the chatty person is actually a problem for himself or herself and a problem for students to cover in exams. For example, look at the part B of the question. Use the solubility curve to find the solubility of potassium chloride at 50 degrees centigrade. You can always extrapolate it. These dotted lines in mathematics are known as extrapolated values. This means that you try to come up for a value at x-axis, or you try to come up for a value at y-axis. At x-axis, you would get to know what temperature it was. At y-axis, you get to know what value of solubility it was in grams per gram or per 100 grams of water, right?
Yes.
We call this extrapolation. You might see the word in marking schemes of different question papers. This word comes from mathematics, from graphs. It's not a chemistry word, all right? So you can always find out the value at 50. It's easy to extrapolate it. And I actually did it for 80 degrees centigrade instead of 50. The value for 50 would be over here, all right? Then the maximum mass of potassium chloride that will dissolve in 50 grams of water at 40 degrees centigrade. What if we have half of the value of water and the value for 40, right? What about that? And moving on, the temperature at which crystals will appear if you cool a hot solution containing 51 grams of potassium chloride in 100 grams of water, right? So now you need to understand that temperature at will the crystals will appear if you cool a hot solution containing 51 grams. Now the crystals have exactly 51 grams. So the 51 is probably this value at 80 degrees centigrade. So if you brought it down from 80 to 0, maybe this can happen, right? As since
So how we can write the answer, like after finding the values?
okay, take a look. The answers are given right over here. For part 1, the graph shows, I'm going to zoom it out so you can see the graph and the questions in the same go. Okay, now you must be able to see it, the graph as well as your answers, right?
Yes.
Okay, so the part 1 tells us the solubility of potassium chloride at 50 degrees centigrade. Look at 50 degrees centigrade, it's a little above 40. So if you exactly count it, it would be 42.5 per 100 grams of water. Gave you the answer. And that's how you're supposed to write your answers. The graph shows it is 42.5. How would you know? Take a look. This one is exactly 40. The next dot is 42. And it's a little in between 42 and 44. 44, this one is 46, this one is 48, this one is then 50. I hope you understand how to work graphs out, right?
Yes.
So if this one value is 10 and this value is 20, and right in between you have these values, right? You'd know that this one is 10, this one means 12, this one means 14, this one means 16, this one means 18, and this one is 20. And so if it falls anything over here, this might be 13, right? I hope you know that already.
Yes.
Good, great. So he worked it out as 42.5. Maybe if you would be doing it, you might be ending up with the answer of 42 grams. Let me tell you that the marking scheme will tell you that 42 grams is also correct. Since the diagram is pretty small, an answer closer to this one can also be taken as correct. So don't worry. You can't always be this accurate. You might be thinking that, what if my answer is 42? Or what if my answer is 43? Fine. These lines are pretty close to one another. So if you consider this as an answer or this as an answer, they give you the leverage of these answers. So if you notice at the marking scheme, they'll tell you anything from 42 to 43 is correct. So 42, 42.5, or 42.6, or 42.8, or 43, all of them will be considered correct. Since these are very small diagrams and it's really difficult to see and calculate your answers. All right. So they
Yeah.
give the leverage, and this is a good thing. We understand this leverage is a good thing. And
Yes.
I hope you agree with me too, right?
Yes.
Good, great. So moving on, part two. Now, the part two suggested maximum mass of potassium chloride that would dissolve in 50 grams of water at 40 degrees centigrade. Now, we do understand at 40 degrees centigrade, we are about at 40 grams, but this is for 100 grams of water. What if they're talking about 50 grams of water? Now they changed the mass of water. Previously, we were doing experiment for 50 grams, for 100 grams, sorry. The question is about 50 grams. So what did they do? They halved the value, right?
Yes.
What are we supposed to do? Now let's look at the answer. From the graph, we can see that the solubility at 40 degrees centigrade is 40 gram per 100 gram of water. Now, from this, we can deduce that half as much, 20 grams, will dissolve in 50 grams. So if they
So,
halve this value, you are supposed to halve your value as well, from 40 grams
oh,
all the way to
yes.
20 grams. So you
Yeah,
need to
yeah.
find a link between these two values, and you are supposed to apply the same link over here.
Okay, what if they give like number between 70 gram? Then how are we gonna do that?
Okay, if they give you a number like from 100 grams to 70 grams,
Yeah.
so 40 grams to what? Now, this can be done by a simple method we call metric method or ratio method. What are you supposed to do? Put the value 100 grams and 70 grams on one side, put the
Mm.
ratio signs, and
Yeah.
then 40 grams and X over here. What we do
Yeah.
is that in ratio method, we simply put the fraction signs in them. So now you know 100 is divided by 70 and 40 is divided by X. What you can do is that you can rearrange their positions. This is known as metric method. X goes all the way over here, 40 stays over here, 40 grams. 70 is multiplied with 40, and 100
Okay.
is divided by them. So I changed three positions. I took X from this side over to that side, and I exchanged its position with 100 grams. I took 100 grams where X was standing previously. And then I changed the position of 70 grams along with 40 grams, and it turns out it multiplies with 40 grams. If it does multiply, I can change the ratio sign in an equal to sign. Now you can go ahead and calculate it. So this zero cancels this zero cancels this zero. The answer for X is simply
We
28
can
grams.
we can directly do it on calculator, right?
You can do it on calculator, that's fine. But since I'm doing it mentally, so I'm giving you an easier way to do it. You can do
Yes.
it in calculator. If you do it on calculator, you'd end up with the value 2800 over 100. And again, the answer is 28 grams, right?
Mm. Yes.
So if you're good with mental maths, you can do it like me, or you can do it at calculator. It's entirely up to you. Remember this
Yeah.
method, we call it metric method. This is going to help you really a lot with these kinds of values throughout the
Yes.
chemistry portion.
Mm. It can also be in maths, right?
Actually, this comes from mathematics, so it will be a part of maths, physics, and chemistry. It may
Yeah.
rarely be a part in biology as well.
No, actually, biology there is no much calculations like chemistry and physics. They have more.
That's why I use the word rarely. The
Really.
calculations would be very rare. Hardly a
Yes.
couple of calculations after 5 to 6 chapters. A couple of calculations, not even that much.
Yes.
All right. So,
Yes.
okay. Now, what I'm going to do is that we're going to stop right